Breaking down an entire muscle into those fascicles and then individual muscle cells, which are called muscle fibers, it's just one level of organization that skeletal muscles have. Muscle fibers are full of those large cylindrical-shaped proteins called myofibrils, and myofibrils have the ability to shorten during a contraction. When all of your myofibrils within one muscle fiber shorten in a contraction, they pull on the sarcolemma of the muscle fiber. This generates tension on the endomysium, and that tension is then transferred through to the perimysium, and the tension in the perimysium is then transferred to the epimysium, which in turn is attached to a bone, and the shortening or the tension or the force that's created moves the bone. And as you can see in this picture, this myofibril has alternating regions that are more densely packed with colors than other regions. It's these myofibrils that have this striated appearance, giving skeletal muscle those striations that we see under the microscope. We call these the light and dark bands on a myofibril. The I bands are areas that are light in color, and the A bands are areas that are dark in color. In fact, some books call these the light and dark bands instead of I and A. What we're going to find is that there is only actin, a small, little tiny myofilament or protein in the light bands. And in the dark bands, there is both actin and its complement protein myosin. Before we look into this picture on the bottom, which is a picture of a sarcomere, let's understand what a thick and thin filament is, and let's understand what actin and myosin are. The thick filament is a myofilament, which is a very tiny protein within the myofibrils of a muscle fiber. And down here, this is a picture of the thick filament. The thick filament is composed of a small protein that is called myosin. And this is a picture of myosin up here. Myosin proteins have a head, and they also have a tail. Actually, they have two heads and two tails that are all wrapped around each other. And you can see here how there's like a hinge area, which allows myosin to kind of ratchet back and forth. Down here at the bottom of this picture, I have what would be called the thick filament. A thick filament is a combination of many hundreds of myosins. And you can see that all of their tails are aggregated together, and they're coming off looking like these little nubs that are coming off the myosin. Have you ever used a ratcheting tool, like a socket wrench? You might be tightening a bolt onto something, and you would use the ratcheting tool to apply torque or force, moving the bolt righty-tighty, lefty, moving the bolt clockwise to fasten it onto whatever you're fastening it, and then you would ratchet the tool back to its original position without any torque that's applied. This is, it's somewhat similar to myosin and its relationship to the elastic protein that's present in myofibrils. Myofibrils basically ratchet themselves into a new position, and then the elastic protein applies force to bring it back into its starting position. The thin filament is a little bit more complicated, and the thin filament is full of a protein called actin. There are other proteins too, but let's start with actin. Actin doesn't have tails and a head like myosin does. You can see the subunits of actin and their spherical little shape in all three of these pictures here. Each of these subunits, so this little thing right here is a subunit. Each of these subunits has an active site. And back in a previous chapter, we talked about enzymes and how enzymes were proteins with a very specific shape that created an active site, where another molecule could connect to them. As you can see here in this picture, in the middle here, that active site seems to be covered with that purple strap, which is called tropomyosin. In the picture at the very, very bottom, though, the tropomyosin has twisted to reveal all of those active sites. And although you can't see it, there is another rod-like protein running down the core of this that the actin subunits are attached to, and that rod-like protein running down the core is called nebulin. To make the thin filament even more complicated, there's also this structure here that I've put, which is called troponin. And I have a picture of troponin here without calcium attached, and then I have a picture of troponin here with calcium attached. Troponin is something like a lock, and calcium is like the key. As you can see from the picture in the center, again, I have my thin filament, and all of the active sites on the actin subunits are covered by tropomyosin. Also note that calcium is not attached to the troponin. When calcium attaches to the troponin, as in the picture on the bottom, it's much like a key that's inserted into a lock. And troponin allows the tropomyosin, kind of like the door, to twist open and reveal the active sites on actin. Take a moment to think about how these thin filaments are embedded in those myofibrils, which are the cylinder-shaped proteins shoved into one muscle fiber of a cell, and there can be many muscle fibers in one muscle organ. As long as you can flood that muscle, the whole muscle, if you can flood it with calcium, then you can be capable of having a contraction because of this complex structure right here. Many of you connect with troponins with patients that may come in with myocardial infarctions or a heart attack. A heart attack usually breaks down these troponins, and their breakdown products are circulated in the blood. We can test for cardiotroponins in the blood to tell if you have had a heart attack. What's frustrating, though, for the patient is that the test can take up to 2 hours. And so as your patient is worrying that they're having a heart attack, their anxiety is becoming worse, creating a positive feedback mechanism pretty much on their heart. No, it's not like I've ever had that done to me or anything like that. No. Okay, now coming back to this picture, let's look at the bottom picture here, which is an arrangement of actin myosin in such a way that it forms what we like to call a sarcomere. A sarcomere is basically the smallest structure in a muscle that is capable of creating a contraction. And look at this myofibril. There are many sarcomeres actually lined up on one myofibril. Sarcomere. So they're kind of lined up like train cars, back to back to back. The complex and specific arrangement of a sarcomere is what allows a contraction to happen. Okay, so the sarcomere, any sarcomere, is bounded by a protein arrangement called the Z discs, right? These Z discs are very, very easily seen on this picture up here of the myofibril. So we can always find the boundaries of a sarcomere by looking for those Z discs. The next thing that you should look is a structure at the very center of a sarcomere, which is called the M line. Right? And even if you can't see it on a histological picture, you can kind of guess where it is because there's this lighter zone in the middle, which is called the H zone, which spans from here to here. You know, some books cover the H zone, some don't. You can see the alternating arrangement of actin myosin. And you can almost imagine all of these little myosin heads here. Let's imagine all of these little myosin heads. Ooh, attaching to the revealed active sites on the actin subunits. This would create a pivot point at which the actin and myosin could ratchet past themselves. But what happens when this structure becomes smaller and the myosin can no longer ratchet past the actin? It's at that point that the muscle has to relax back to its original shape. And it's these elastic fibers here that allow that to happen. So to make a contraction, you need force and tension. But to allow that contraction to go back to relaxation, you just need these little springy elastic fibers here that are usually called titin. And I'm sorry, I should have put arrows. When you create force and tension, what happens is the Z lines move closer together. The actin and myosin overlap to a greater extent, and that is how a contraction is created. And the shortening of a muscle that brings one bone closer to the other bone in a contraction.